Today, let's dive into a sheet of aluminum foil and look at its nuclei.
The foil contains the septillion aluminum atoms. Deep inside an atom is its tiny nucleus, holding the majority of atom's mass, densely packed with 27 nucleons, including 13 positively charged protons and 14 non-charged neutrons.
The mass of the nucleus is less than the sum of masses of individual nucleons. The difference, delta M, or mass defect, is convertible to the nuclear binding energy, delta M multiplied by c squared, which is the amount of energy required to break apart the nucleus. A useful model in explaining E sub B is the liquid drop model. The nucleus is seen as a drop of liquid of nucleons, held together by the strong nuclear force. The formula based on this model to estimate binding energy contains 5 terms. The first term accounts for the strong attractions among nucleons due to nuclear force. It is proportional to the volume or mass number A. The second term arises because a nucleon on the surface of the nucleus receives fewer attractions than an interior nucleon due to having fewer neighboring nucleons. Thus, the binding energy needs to be negatively adjusted, and the adjustment is proportional to the surface area, or A to the power of 2/3. The third term accounts for the electrostatic repulsion between protons, which makes the nucleus less stable. This negative Coulomb term is proportional to the number of proton pairs, and inversely related to the average distance between two protons. If N and Z are not equal, the surplus particles are filling higher energy levels, increasing the total energy of the nucleus and decreasing the binding energy. Asymmetry term accounts for such reduction in binding energy. Protons or neutrons are more stable in pairs. Any unpaired nucleon reduces nucleus stability and binding energy. The last term, or pairing term, accounts for such adjustment. This 5-term formula is semi-empirical because all the coefficients come from experimental measurements. The formula helps determine the most stable nucleus. A higher binding energy per nucleon means greater stability. According to the equation, binding energy per nucleon peaks at a mass number of 56, which matches experimental data. Thank you for taking the dive with me. See you next time!